Okay, so this is problem 7.21 out of Griffiths Introduction to Quantum Mechanics, Edition 3. And before I get started solving this problem, if you'd like to see more, please give the video a like and subscribe. I'm going to keep going through and working through these problems that were assigned to me as homework, and I'm just kind of studying to prepare for an exam, and if it helps people along the way, that's great. Alright, so 7.21 is kind of a longer problem. We're looking at the transition between the n equals 3 and n equals 2 state. And it kind of has us do a few things, but before I even get started with that, I kind of want to just talk about the quantum numbers a little bit, just to get it out of the way. So n is your principal quantum number, which is associated with our energy. L is your orbital quantum number. And that has to do with angular momentum. S is your spin. And kind of depends on the particle you have, but for right now, we'll just think of it as being plus or minus a half. And J is the total angular momentum. So you can think of J as being the spin plus the angular momentum. So that's what the total angular momentum is. And then we have some other quantum numbers. M sub L, that's the magnetic orbital. Which can take values between negative L to positive L. You have M sub S, and that's the magnetic spin. Which again, we're just going to think of as being plus or minus a half. And then we have M sub J, which is the magnetic total. Magnetic total angular momentum. So we're going to go through all these different quantum numbers and a bunch of these problems. I just wanted it to be clear what it is that we're actually looking at. So just getting that out of the way. Alright, so let's get started with the problem. The first thing the problem asks is, it says, first of all, determine the wavelength and the frequency of the line according to Bohr theory. Okay? So wavelength. We'll start with that. And what we need to know is that your energy is equal to hc over lambda, where h is just Planck's constant, not the reduced constant. Okay, so then what we can say is the wavelength from this change in energy. So we're doing the naught to indicate it's the Bohr theory. And then just a little bit of algebra here. Lambda is Planck's constant, c the speed of light, over this. Okay? And in general, with Bohr's theory, E sub n is equal to minus 13.6 electron volts over n squared. Okay? And hc, just the way that I remember it, is 1,240 electron volts times nanometers. Okay? So lambda equals 1240 electron volts times nanometers divided by minus 13.6 electron volts times 1 over 3 squared minus 1 over 2 squared. Okay, so far looks good. The electron volts will cancel, we'll get nanometers, and this number is going to be bigger than the other, so that means the negative sign will go away. And when you plug this in, you should get about 656.47 nanometers. So that's the wavelength. That was the first thing they asked for. And the second thing they asked for was the frequency. Okay. And this is actually pretty easy now because lambda is equal to c over the frequency, which means the frequency is equal to c over lambda. And we obviously just found this wavelength, but I'm going to convert to meters because c is meters per second. Remember, this is meters per second, and we want units of 1 over second, so we need that to cancel. And when you plug that in, you should get 4.57 times 10 to the 14 1 over seconds, which is just a hertz. Okay. So that was the first part of the problem, and now let's look at the second part. So the second part says, determine how many sublevels the n equals 2 splits into and find the fine structure for each of these in electron volts, and then do the same for n equals 3. Okay. So we'll start with n equals 2. For n equals 2, we know L is equal to n minus 1, or can be less than equal to, but also positive. So then L can be 1, and then that means M sub L could be negative 1, 0, 1. And then J, remember J is your L plus your M sub S. And we know M sub S is plus or minus 1/2. So it could be J plus 1/2 or J minus 1/2, which means J can be 1/2, J can be 3/2. So 2 possibilities for J. And now I'm actually going to go in the book here to get the equation because I don't have it on me. We want to get right here. So I'm just going to screenshot this and insert it here because I could use that equation because I don't remember it. And I'll include that one too, but I don't think that'll be useful. Perfect. We have this guy. So we can calculate the fine structure, which is the second part. I don't know if I read that, but it also mentions, oh yeah, find the fine structure. Oh, okay, so that is the equation we're going to use. And we have 2 possibilities for J. To start, we'll do J equals 1/2. Then the fine structure will be minus 13.6 EV over n squared, but we said n was 2, so that's 4. Yes, and then this is all squared. sorry, that square kind of confused me for a second, times 1 over 2 mc squared, 3 minus 8 over j, so this will just be 1. And remember that mc squared is the rest energy of an electron. Rest energy of the electron, because that's what we're interested in, which for that is 0.511 times 10 to the 6 electron volts. Okay. So that's good because we have electron squared in the numerator, so we'll be left with just electron volts squared in the numerator. So we'll just have electron volts, which is what we want. So just plug this into a calculator. Make sure you multiply the rest mass energy by 2. And when you do that, you should get a minus 5.66 times 10 to the negative 5 electron volts. And there was also the possibility of J equals 3/2. And you can just do the exact same thing here. Not really much changes except for 3 minus 8. And now it's 3/2 plus 1/2. That's all that changes. Okay. Which is just 4/2, which is just 2. So this is just 4. So this is just minus 1. Okay, and when you plug that in, you get minus 1.13 times 10 to the negative 5 electron volts. So that was for the n equals 2 state, but there was also n equals 3. Not m, n. And L could be 2, 1, 0. So m sub L could be minus 2, minus 1, 0, 1, 2. M sub S is still plus or minus 1/2. That doesn't change. And then when we add these together, you could get a J value. Well, J could be 1/2. And J can be positive. It can't be negative. I forgot to mention that. Doesn't really make sense for it to be a negative number. So we're only taking J be positive. So you could, technically for both of these, J equals negative 1/2 could work, but we're going to exclude the negatives. Okay, so 1/2 is a possibility for L equals 0, MS equals 1/2. 1, if L equals 1 and MS is 1/2 or negative 1/2, you'll either get 1/2, which is already accounted for. That's degeneracy. Or 3/2. And then 2, again, if it's minus 1/2, then there's not really much to do there. But if it's positive 1/2, you get a new sublevel of 5/2. Okay? So those are now 3 J values to consider. So we have J equals 1/2. Now the only difference here is when we do the fine structure energy. Instead of dividing by 4, because now n equals 3, this is 9. Times 1 over 2 mc squared. We know what mc squared is. 3 minus, and now it's 4 times 3, which is 12. Over 1/2 plus 1/2, which is still 1. And then plugging this in, you get minus 2.01 times 10 to the negative 5 electron volts. And we can do this again for J equals 3/2. I'm sure you guys are kind of comfortable with this, so I'm just going to plug in what you'll get. The only thing that changes is this was 1/2. plus 1/2. In this case, it becomes 3/2, and then you plug it into a calculator. When you do that, you get minus 6.70 times 10 to the negative 6 electron volts. J equals 5/2. That 3/2 just becomes a 5/2. And your fine structure energy is minus 2.23 times 10 to the negative 6 electron volts. Okay, so let's see. Now it wants us to draw an energy level diagram showing all possible transitions from n equals 3 to n equals 2. Okay, so I'm going to try my best to draw something out here. Let's do this. So this we could say is E3. This is J equals 5/2. J equals 3/2. J equals 1/2. So you can see the energy is being lowered more and more depending on your J value. So this can kind of space off to here, or here, or here. And then we also have an E2, which drops down to just 2 levels. And this is J equals 3/2, J equals 1/2. And then if we want the energy levels going from 3 to 2, let's get an arrow. You could go from 1/2 to 1/2. That's a possibility. You could go from 3/2 to 1/2. That's another way to get there. Or just 5/2 to 1/2. Either way, you're going from the E equals 3 energy level to the E equals 2. And then we can do the same thing, but instead of going to the 3/2, we go to the 1/2 level, because that's a really thick arrow. Let me lower that a little bit. Okay, so you can count these up. Pretty easy to see there is 6 transitions from n equals 3 to n equals 2. Okay, so hopefully I should probably connect these. Alright, so with that out of the way, what else do they want us to do? Let me just draw an energy level diagram showing all possible transitions from this to this. Okay. Find delta E and EV for each transition. Okay. So now we found all these different transitions. Let's find the delta E going from each one. So we'll do, say, the first one, which is the J equals 1/2 to J equals 1/2. So this is this first green arrow. That's the first transition. They want us to find the change in energy. I'll just call E31 minus E21. And it's pretty easy to do. We're just going to use our fine structure, just like we were doing earlier. So I'm going to plug this in, minus 13.6 over, so we're using this equation. I'm just doing, maybe it'll make more sense if I label it like this. Free structure, 3 to 2. I don't, maybe my notation's a little messy, but hopefully it makes sense what I'm doing. Over n squared, well, n is 3, so that's 9. This is squared, times 1 over 2 mc squared. 3 minus 4 times 3 is 12. J plus a half, well, j is just a half here, so this is 1. But I'll go ahead and write it out just so you guys see. And then the difference of that minus negative 13.6 over, so now n is 2, so n squared is 4 squared times 1 over 2 mc squared. Sorry, the first transition is going from 1/2 to 3/2, not 1/2 to 1/2, my bad. 3 minus, so 4 times 2 is 8, over 1/2 plus 3/2. And you can see this will get a little easier because every term is going to have this number squared in it. There's going to be a 2mc squared in it. So I'll just call that x equals that. So delta E equals x over 1 over 9 squared times 3 minus 12, so 9. And then minus 1 over 4 squared, 3 minus 8, 1/2 is 3/2, which is 4/2, which is 2, so 4, so minus 1. And if you plug in what, and remember mc squared is the rest mass energy of an electron. If you plug all that in, you get minus 8.80 times 10 to the negative 6 electron volts. So that's the first one. And the second one, you could go from j equals 3/2 to j equals 3/2. So that's the second green arrow. And you can see that it's going to follow a pretty similar process. So the only difference here is one of the j values changes. So instead of this being 1/2, this would be a 3/2. Let me unhighlight that so you don't get confused. But so anyways, delta E equals E fine structure 3 minus E fine structure 2. We'll use that same x value. 1 over 9 squared, 3 minus 12 over 1/2 plus 3/2, minus 1 over 4 squared, 3 minus 8, 1/2 plus 3/2. So it gets a little repetitive here, but that's okay. And when you plug this in, you're going to get 4.61 times 10 to the negative 6 electron volts. And you just kind of keep going through all 6 of these. Don't know if I'm going to go through all of them, but I think you guys kind of get the picture. So in this one, this would be J goes from 5/2 to 3/2. So this is the last green one. And again, you're just plugging into that equation. So I'm going to just tell you what delta E is. And if you plug these values in, you should get 9.08 times 10 to the negative 6 electron volts. I hope you guys are all right with that. You're basically just plugging into this big equation. So the calculator should do it for us. So the fourth one, now you can go from J 1/2 to J equals 1/2. So now this is the red arrows. So we'll go 1/2 to 1/2, 3/2 to 1/2, 5/2 to 1/2. And the delta E here is 3.64 times 10 to the negative 5 electron volts. For the fifth one, again, J goes from 3/2, J goes to 1/2, and we're finding that energy change there, which is 4.99 times 10 to the negative 5th electron volts. And then for the last one, so this is for the sixth energy state. So this is, this is J equals 5/2. J equals 1/2. And delta E is 5.43 times 10 to the negative 5 electron volts. Okay. So that is the delta E. And it says finally convert to photon frequency and determine the spaces. Okay. So now we want to find the frequencies of these transitions, basically. And the way to do that is to recall that your energy is equal to your frequency times Planck's constant. So just solving for that, E over H. Okay, so if you want to find the change in frequency from 1 to 2, that's the change in energy 1 to 2 over H, just 3.23 times 10 to the 9th hertz if you plug that in. And you can do the same thing, now 2 to 3. And if you plug that in, you'll get these different values. So this is really just plugging in, to be honest, nothing crazy here. I'll just go ahead and give you the answers in case you want to check your work. And those are your changes in frequency. So there's a lot of different stuff going on here. First, we found our wavelength between these two energy states and the frequency. And we could compare our wavelength and frequency if we wanted, but anyways. So then we found our different subsets of energy for n equals 2 and n equals 3 with J. And then with that, we found our fine structure energy correction for these different values. We drew a diagram and indicated the 6 transitions from n equals 3 to n equals 2. And then we found the change in energy from each one of these transitions. And then we found the frequency between these transitions. So hopefully that makes sense. If it did, please like the video and subscribe, and I will post more videos soon.